How do we measure it? Well, in all cases, in order to measure biodiversity, you actually have to go out and sample. You have to count species, identify species, and count species. And it's hard work. It requires not complex equipment, but it requires sometimes a lot of equipment. Some measures of biodiversity are fairly simple, just the number of species. Other indices have been developed, though, that help us understand how the number of species really is changing. A lot of them are pretty complicated mathematical models. They work in probabilities, but they all depend on knowing what the species is and how many of each one there are. I'm not going to spend a lot of time explaining, actually I won't spend any time explaining these because they really do make my head spin. But I will simplify it a little bit just to try and explain what I'm talking about. Let's say I walk to the beach, and I put a net in the water, and I caught 4 hermit crabs. That's all I caught, 4 hermit crabs. What could I say about the diversity of my sample? Well, I caught 1 species. Probability of me, if I went back there to sample again, probability of me catching another hermit crab is 1 or 100%. That's just a mathematical probability, unless I took them all. And an index, something like Simpson's D, which sort of expresses probability, would be 1. And that's a fairly low number of Simpsons means low diversity, higher numbers is higher diversity. If I went back to that same beach a year later, threw the net in, this time I catch hermit crab, rock crab, scallop, and a green urchin. What can I say about the diversity now? Well, gee, I caught 4 species. It seems more diverse. The probability of me catching those 4 species again, or any one of those 4 species, is 1 in 4. 25%. I'm curious enough, the Simpsons D, the diversity index, would say 4. So it's saying, yeah, diversity is increased. It's 4 times more diverse than the previous one. And by chance, because it's an even distribution of species, so I caught the same number, it happens to be exactly, or it's reflecting the probability. Now here it gets a little bit tricky. I go back again. And this time I'm catching 3 times as many scallops as I'm catching hermit crabs, rock crabs, and urchins. What do I say? Well, I caught 4 species again. This time the probability is a little bit mixed. If I want to catch a hermit crab again, or find out what my odds of catching hermit crab, it's 1 in 6. If I'm thinking about scallops, it's 3 in 6, or half. And something like a Simpson's D, a diversity index, would reflect that change in proportions, so that now the diversity is a little bit less than the previous sample where they're all evenly distributed, because the sample's being dominated by scallops. I hope that was easy enough to... It's easy enough for me to understand, so it's got to be easy enough for you to understand. Okay, so that's a little bit how you go about measuring and describing diversity. And then how would I use that? Say, it's important to have indices like this so we can monitor how things change over time. So this is just a simple graph of some index number here over time. If I went and repeatedly sampled there, the species number might stay the same over 3, 4, 10 samples. But the proportions might change. So what you would see is a change in the Simpsons, something like a Simpsons index. Part of that would be just natural. Part of that might be actual, some kind of real change. But it wouldn't be reflected in the species number until we probably saw a sustained drop in the Simpsons index. And only then would I actually see a change in the number. So it's not just the number of species that counts, but it's the proportion of species that counts and helps us describe diversity and measure diversity in a particular area. So let's go on to some of the projects that I've been working on. Let's first talk about a biodiversity trawler we're doing in Passamaquoddy Bay. Fortunately, we have an historical sample to work from. 30, 40 years ago, there's some scientists at Fisheries and Oceans that went out and did some sampling for fish in the Passamaquoddy Bay area. And all the little yellow pins here represent the sites that they either took a beach seine, like this, or they used a gill net, and couldn't bring a gill net, or a trawl. So they would have beach seine along the shorelines here. They would have put gill nets in areas like here. And they had 3 trawl sites, site A, B, and C. 2 inside the bay, 1 outside, and there was actually another trawl site here, just right outside of the river. So this is an opportunity. We've got some historical information. It's an opportunity to see how diversity changes over time. So one of the projects that I started in 2009 was to go back to these 4 trawl sites, A, B, and C. Tried sampling the same way that they were sampled 30 years ago, and see what kind of changes This is one of the vessels we use. This is a Coast Guard ship, Biodiversity. It was commissioned, it's brand new, commissioned in 2010, 60 feet long, 36 metric tons in displacement, 988 horsepower. It's a very powerful boat. Maximum speed 15 knots. Cruise 3 and it holds 7 scientists, so it can get heavy water. It's particularly busy when we do that. So it's a great, great boat. Unfortunately, and what we do is we strap an old trawl to it, like this demersal trawl, and we ask it to go in a perfectly straight line at 2 knots. Not, it's hard for the crew to really get excited about that, but that's part of it. This is just a diagram of what a demersal trawl is. Essentially, it's attached to the stern of the ship, and it's dragged on the seafloor. And it's ideal, it's really designed to catch groundfish, but it also will catch just about any species that's on the bottom. So, have the trawl out for about a half an hour, bring it in, caught in's full. Great. Caught in comes over to the hopper, and we open up the bottom, and release our catch. And then the work starts. This is Nathaniel, who's one of the people that work with me out there, and he's giving me the look saying, "Are you kidding? This is going to take us all day." And it literally does take us all day. One of the first things we do is we sort out what we catch and start identifying things. Species like this is a large, berry female. These ones are usually sorted out first because we use them for other research in labs. So we'll take them back to the wet lab and we'll have other scientists use them for these types of research in terms of feed production and productivity. So they're what we take care of first. And then we begin the long sorting process of identifying everything and dividing it up. We start counting them. We measure them. We weigh them. And then we do it all over again. We do some counting, more sorting, and more sorting. And what you'll notice here is that the crew changes, like there's not really the same people in every shot. I have a really hard time keeping people to help help once, and then they say that's it, because by the end of the day, when all the sorting is done, this is pretty much what happens. We never come back. Anyway, why would we sample so much? Why do we want to go out more than once? Well, the reason for that is because biodiversity science is a very difficult business. If you go out and sample once, there's no guarantee that you're going to get all the information you need. You're not going to be able to capture every species that's in that area on that day. So this is just a diagram. This is exactly what happened in 2009. It's just a history of our sets. And it's just, it's just This is just the number of new species that we caught. The first set, we only caught 7. And remember that set because it was full of shrimp. Hardly anything else. It was just chalk or block full of shrimp. Our second set, we caught 20 species, including those 7, so it's an accumulation. Third set, 24, and so on. Up to the point where when we got to the 5th and 6th and 7th set, we weren't really seeing any more new species. And so this is telling me by the time we've done this, we've sampled sufficiently to get a feeling for what's the biodiversity of. This is all that we're going to catch with this gear in this time. So it's important to sample enough so that you can do a comparison between one year and the next. Because if you're only sampling down here, you don't know whether you just got lucky or not. So we always need to do repetitive sampling to get up here where we're not getting any. This is abundance of the top 10 species in 2009. Essentially, it's a snapshot of what we caught. And as I said, it was full of northern shrimp.
Are those Pandalis shrimp? Northern shrimp, same thing as Pandalis shrimp?
Yeah. Pandalis borealis. And so this is just a pie chart showing the proportions of what we caught, and you can see a good proportion was northern shrimp. We also caught some herring and cucumbers and potatoes and other species of shrimp. This is 7 set. We only caught 37 species, and our Simpsons diversity index was about 1.5. Really staying not very diverse, guys. What happened in 2011? Just last summer. A little bit of a different picture. We did just about the same number of sets, a few more. We're pretty sure we, again, the collection has to do, but a really different picture as to what we were able to catch. Again, northern shrimp dominate, but we're also seeing a lot more herring, scallop, winter flounder, and a montague shrimp in our set. We also caught more species, 66, and the diversity index increased from 7 to 7. Now, the historical data only looked at fish, so I had to kind of simplify what we were catching in 2011 and 2009 to just look at fish. So this is the top 10 fish species over 2 years. It's just like David Letterman. So smelt, herring, winter flounder are really the dominant species in 2009. They're also pretty dominant in 2011. There's a little bit of variation, but really, the 2 samples are about 80% similar, and the only differences that we saw in these top 10 were the dominance of little skate and cod in the 2009 sample being replaced by haddock in the 2011. That's not to say these species weren't here, they just didn't make that top 10 list. So really pretty similar samples, a little bit of variability in terms of just the top 10. But when you look at all the species combined, you see big differences in terms of number of species and diversity. How does that compare to 30 years ago? So sampling that was done in 1976 and 81. This is the top 10 species. Winter flounder, herring, silverhead, the top 3. 2009 and 11, herring, winter flounder, and smelt. I won't go through the whole list, but really now we're seeing a 40% difference in the top 10. Species like American plaice, ocean cod, dogfish, little hake, and juvenile pollock, which made the top 10, then aren't really making the top 10 when we combine these 2 samples. They're replaced by smelt, alewife, hake, redfish, haddock, and blue. So what we need to do next is really we need to continue some sampling to see what kind of year-to-year variability we have, and really try to get an understanding as to what this difference really means over the last 30 years in terms of why are these species different? Is it something that's happening locally, or is it something that might be on a more regional or global scale? So what do we learn from the biodiversity trawl? We learned that we have to sample more than once in a year to get a sufficient number of species in our sample. We also know that there is some natural variability from year to year. And we can also see some long-term change from our historical data. But this is going to require a little bit more work. It's going to be hard work and some persistence, but we're pretty sure we're going to gain some insight if we look at the